This video is going to be about a specific topic in differential equations, and actually it's going to be a tool to help you do a specific topic in differential equations, and that topic is solving a linear ordinary differential equation using infinite power series solutions. For example, if I have the first order linear differential equation y prime minus 2xy is equal to 0, I can actually make the substitution by the power series for some function f of x, a sub n, x to the n, from n equals 0 to infinity. And then y prime, for example, is going to be the sum of n times a sub n, x to the n minus 1, from n equals 0 to infinity. This is just following the power rule, treating n as a constant and a sub n as a constant and differentiating with respect to x. The first term is going to be, for if we plug in 0 into this expression, 0 is going to go in for n, so 0 times this is going to be 0. So this is actually equal to from n equals 1 to infinity. We just move that index up 1. And so we can take these summations and substitute them into the original differential equation, and then combine all series as 1 and find a solution in terms of infinite series. So I assume that this is the background knowledge that you have, and that the only trouble that you probably have is the long process of combining multiple series with different starting indices and with different powers of x together as a single series where all of the powers of x are n and all of the starting indexes are the same. They don't have to be 1 or 0, they just have to be the same. For example, if I have the sum of n times a sub n, x to the n minus 1, n equal 1 to infinity, and then we have minus 2 times a n of x to the n plus 1 from n equal 0 to infinity, and I want to combine them together to get. So what this video is about is me showing you a shortcut to be able to get from here to here very quickly with very few lines of work, and this tool will help you to make very few mistakes and not forget anything as you go. To better show you how to do this using this approach, I'm going to just start with a more complicated example. Let's assume that we've already done all the steps to substitute these infinite power series n for the unknown function and its derivatives into a linear ordinary differential equation, and we get these summations, which we want to combine as 1. What I use is a matrix to write down the starting indices of all of the summations, and I also write down the starting powers of x. So a 4-row by 2-column matrices. So the starting index of the first series is 2, the next one is 2, then 1, then 0. And then we have power of x is n, n minus 2, then n here, and then n. So our first goal is to make all the expressions here n. So what do I have to do to make this n? All I have to do is add 2. The plus 2, and whatever I do here, I have to do the opposite here, minus 2. Now I'm going to rewrite this matrix and call it the final matrix. What I'm going to do is just simplify the left column. I'm going to keep this plus 2 here for later on, and you'll soon see why. Now we look at which is the highest number in this column. That is going to be the starting index of our final sum, in which we've combined all of these together as 1. But before we get started with that, let's start writing the first series and then work our way across. In this case, this row represents this series, this row represents this series, and so forth. Whatever we do to the right hand side, we have to make that substitution in for n inside of the summation that it corresponds to. So for example, in the first row we did nothing to n, so therefore we just rewrite all of this expression. Then we write the next series. This one is going to be different. We have the sum of, we're going to say, n plus 2, n for every single n in the expression. And since we didn't do anything to the last two series, we can just rewrite them and just change their starting indices to 2. Rewriting this line, we can see that this simplifies to, so I'm going to delete this now. The last step is to extract terms from the series. And with this approach, you really don't have to struggle that much to know exactly from which series you extract terms and exactly what terms those are. That is, we look at the first column of the final matrix and we see that the starting index should be 2. So for every single row in which it doesn't have the highest number, which is a 2, we add terms from. So for example, we don't add any terms from the first series, so this is fine. From the second series, we're going to add a term for substituting n equals 0, and we're going to substitute a 1 into n into this expression and extract that from this series. So we do the same for the next. For the third one, we only have to substitute 1 for n in the expression in here. And of course, I forgot that we have a minus sign here, so we have to put a minus sign there. And then finally, for the fourth series, we repeat the same process as we did for the second. So we add the extracted terms, and all of this is now equal to 0. We can simplify these terms now algebraically and combine like powers of x, and we can also put all of these expressions into the same summations, since they all have the same lower limit and upper limit. I'm now going to conclude with one final example. In this example, the starting index of all of the summations in which we want to combine are the same, but the powers of x are different. How does that work? You'll probably encounter a problem like this later on in your textbook, beyond just the introductory section on this. But we can see that the first and third series, the power of x is n plus r, but the second series is n plus r plus 1. However, all the starting indices are n equals 0. How do we combine these as a single series? Well, it's simple. We just use the same process that I showed you earlier. So we're going to have a 3 by 2 matrix this time. We have 0, 0, 0 for these zeros, and we have n plus r for the power of x in the first series, n plus r plus 1 for the x in the second series, and n plus r for the x in the third series. For this section, what we want to do is make all of them n plus r. So therefore we subtract 1 from this row, and therefore we add 1 in the left column. We rewrite this matrix as our final matrix, and we simplify the left side, and we can see that it's the same process as before, where we have the highest number in the first column to be 1. That means that the starting index of the combined series is going to be 1, and we're going to have to extract terms from the first and third series respectively. So what we do is we rewrite the first one, then we add the second summation where we substitute n minus 1 for every n. So it's the same process. It doesn't matter what expression you're trying to match every single power of x to. You always substitute n plus whatever integer you have here in a different color font or however you indicate it to get this. And we add the third summation from n equal 1 to infinity. And we put equals 0 below here because now we're going to be extracting terms. So what series do we extract terms from? Well, it's the same as before. We look at the left column of the final matrix. If this number is less than the greatest number in the column, then that is a series which we will extract terms from, and how many of those terms we extract are determined by this number, the difference between this number and the greatest number. In this case, we're only going to extract 1 from here because 1 minus 0 is 1, that's the difference, and the same here. Since this row represents the first series, we add the expression of the first series with 0 substituting for every single n. And of course we substitute 0 for n because the index or the variable of the summation is n. And finally we add 2 times because we're extracting terms from this one, and we substitute 0 for every n in that expression equals 0. So in summary, I've shown you 2 examples, one in which the starting index of all the series that we want to combine together as 1 are the same, and in the first example we saw that things can get complicated. Their indices are all different here, but we know how many terms to extract from our series and which terms to extract and how many to extract just by looking at this simple matrix. Lastly, take note that this is identical to the traditional method. It's just like a synthetic division versus long polynomial symbolic division. It enables us to not make any mistakes, and it saves the amount of written work we have to do. Therefore, I hope this video has been helpful to you, and thank you for watching.